So lesson 9, today we're going to talk about electronegativity. And electronegativity is something we talked about earlier. There's a number associated with electronegativity. It's on your periodic table. And you probably should get your periodic table out today. So you can see those electronegativity values and the trends that go with those numbers there. Okay? The nucleus of an atom is positively charged and therefore attracts electrons, which are negatively charged. So if you think about the nucleus, there's a bunch of protons and neutrons in there, but there's a bunch of positives, and those positives attract all the electrons around it. Okay? The definition of electronegativity is something that you will want to know. It's right here. So the electronegativity, En of an element, so when you see that term En, you'll know that you're talking about electronegativity of an element, is the relative measure of the ability of that element's atom to attract the shared electrons in a chemical bond, which is kind of wordy. Basically what we're saying is, or what electronegativity is, the ability to attract electrons. And it could be electrons of its own. It could also be the electrons in a shared chemical bond, like for example between nitrogen and hydrogen, for example. If there's some shared electrons there, how well are those electrons attracted by the nitrogen or the hydrogen in some cases? If you look at the electronegativities range from 0 to 4. 4 being the highest, obviously the best at attracting electrons, 0 being not at all. Not at all. Which ones don't want to attract electrons? Well, mostly, of course, noble gases, right? They're stable, group 18, stable already, has a full octet, doesn't want to attract electrons, okay? So they have usually electronegativity of 0. The metals, of course, usually have lower electronegativities, and the nonmetals usually have higher electronegativities, all right? So there is some trends here you'll see. Higher electronegativities indicate a greater attraction for electrons. What is the best nonmetal for attracting electrons? The best nonmetal at attracting electrons? No. I'll give you a hint. If you have your periodic table out, it's the one with the highest electronegativity. Fluorine. Okay? Remember we drew fluorine a while ago? It's been a while. We drew francium on the same day. Fluorine, remember, is basically the atom that has 2 electrons and then 7, and it is the best. It's the one with the nucleus closest to the outside energy level that's able to gain that 1 electron. Okay, and I'm going to draw it again here today, and you'll see that. Okay. So higher electronegativities indicate a greater attraction for electrons. Electronegativities increase as you move across a period. So as you go from left to right, look at the values. Just look at your periodic table. This is not, might ask you this question someday. This is easy. You just look at the periodic table. As you move from left to right on the periodic table, what do you notice about electronegativities? They tend to generally increase, yes? Because we're going from something metal to something very non-metal, or metal to something very non-metal. So obviously, okay, electronegativities are going to increase. The ability to attract electrons is going to increase. All right. As you go down a group, electronegativities tend to decrease. Okay, they tend to get a little bit. It becomes harder, and we'll look at that as well. But once again, if I ask you that question, you can simply look on your periodic table. Look at group 1. It goes from hydrogen, well, hydrogen's a little bit of an anomaly, but nonetheless, 2.2 down to, I don't remember, lithium, 1, sorry. Sodium's 0.9, potassium's like 0.8. It starts to generally go down until you get to francium, which is 0.7. All right? So those two there you can just see right on the periodic table. This one here, noble gases don't have En values. There's in fact one that does, but generally we say that they don't naturally want to form bonds. They don't naturally want to attract electrons. Their ability to do that is not very great, so basically 0. Okay. This you guys already have for notes, so that should be okay. But size and electronegativity. So we're going to talk a little bit about size today, and we have to be careful that we don't get confused between size and weight. Okay, I'm going to skip this part right here, and I'm just going to go down to here, and we're going to draw lithium here. Let's do a Bohr diagram. Don't forget how to do these, please. We might have another little challenge on that one of these days here. Let's see, 2. And there's lithium. 3 protons, 3 electrons. Okay, so 3 protons, 3 electrons. Got a weight of 6.98. If I skip all the way over here to fluorine, 9 protons and 10 neutrons. Yes, there's the nucleus. There's 2. And there's my 7. Okay, valence electrons in this case. This is all taking place in period 2, yes? Is what that's called. Period 2, all that means is basically they're in the same period. Look, there's lithium, there's fluorine, same period, same row. All that this means basically is they have the same number of energy levels. Okay, they both of these have 2 energy levels. All right. Now we're going to talk about the size of these, and what we have to make sure, like I said, is that we don't get confused with weight. Which one weighs more? It's not a trick question. Yeah. Cool. Fluorine weighs what, 19-ish, roughly, yeah? Well, it is 19.0, I think, eh? Lithium weighs 6.98 on average, 7-ish. Okay, so fluorine obviously weighs more. I'm not talking about the weight. I'm talking about the actual size. So if you put these atoms down side by side, and you looked at the top from these 2 atoms, so I looked at lithium, and I look at fluorine from the top, and I just say which one's bigger, which one's smaller. Well, what we need to talk about is something called the atomic radius. The atomic radius starts in the middle here, basically of the nucleus, and goes to the outside here. And we would call this the atomic radius. Now, that changes slightly because remember, these electrons, we're drawing a Bohr diagram here. These electrons, they're a little bit further, a little bit closer at times. They usually have a specific energy, but not necessarily exactly on that ring at any particular time. And this one here also has an atomic radius. They all do, by the way. Atomic radius here. When you think about atomic radius, think about circles, of course, in math, whatever, the radius, right? When you actually look at these 2 radii, I guess is the plural, but radiuses. If you actually looked at the radiuses or the radii, okay, you would actually, and you compared those, what you would find is, if you looked, or if you want to say it this way, if you look down on both of these atoms, that fluorine is actually smaller in size. So this is actually smaller radius, and this is a larger radius here. Now, how much smaller or how much larger is it doesn't matter. Okay, we don't need to get into that right now, or for that matter until for quite some time probably. But fluorine, if you actually look at the atom, it's quite a bit smaller, relatively speaking, of course, than lithium. Okay, if you look down on these 2, the size, the actual size, how much space it takes up, is a lot more packed together. And the reason is simply this. Look, what holds these 3 electrons here in this orbit? It's, of course, what? The 3 protons in the nucleus, right? Opposites attract. So the 3 positives attract these 3 negatives. That's what holds them together, yes? Okay. We've talked about this before. So 3 positives, 3 negatives, there's some attraction there. What about 9 positives and 9 negatives? Are you going to have more attractions between 9 positives and 9 negatives than 3 positives and 3 negatives? Yes? I think so. Okay? So 9 positives, 9 negatives, a lot more attraction. And because there's so much more attraction, and of course what this does is it condenses the atoms. So those 9 positives There's more positives, there's more negatives, and it shrinks it down. It draws it in closer together because there's so many more attractions between 9 positives and 9 negatives. So it shrinks it down, and that's what it tells you right here. The more protons and electrons in fluorine, the greater the attraction between the positives and negatives, and thus it condenses the atom. Actually brings it in a little bit closer. Okay? Now, is it half as much? No. Okay? Pretty much guarantee that. But is it smaller? Absolutely. And the general trend is, as you move to left to right on a periodic table, the general trend is, when I ask you this, which one's larger, which one's smaller, the general trend, obviously, that people think, oh, well, fluorine's bigger. Well, it weighs more, but actual taking up the space part, if you look at it, how much space does it actually take it up? What does that sphere look like? It's smaller. Okay? So the general trend as you go from left to right is atoms tend to be smaller as you move left to right. Now, you can describe that however you wish. You can say the radius gets smaller. You could say the diameter gets smaller. Okay, same thing. You could just say it gets smaller. Okay, they get more compacted together. It gets more condensed. Okay, and that's important for us. All right. So that's the first thing about electronegativity and atoms. Okay, electronegativity and atoms. So that's the trend that goes from left to right. Okay. Now, what's the trend as you move down a group? As you move down a group, okay, lithium, 3 positives, 4 neutrons. Okay, looks like that there, of course. Sodium, is 11 positives and 12 neutrons. 2. And 1. Okay, 2, 8, and 1. So as you move down a group, hopefully it's fairly easy to see that this here, to the outside part, of course, once again is your atomic radius here. And that radius there is most certainly going to be smaller than this one here. Or sodium is going to be a larger atom, okay, than the lithium is. It's always going to be like that. And we're not comparing the same thing anymore. Okay, we're comparing something that's in period 2 here to period 3. Well, period 3 implies that we have 3 energy levels. Period 2 is 2 energy levels. So which one's bigger? Well, the one with 3 energy levels is bigger, right? Think about, we drew this before. We drew lithium, we drew sodium, we drew maybe potassium. Remember francium? How big was that? Quite big, right? It took up like this much on the board. Remember? There was 87 protons, 87 electrons. I probably missed a few somewhere. It was like this big, right? So obviously this one is bigger than this one, right? That's not a shocker to you. The more energy levels you have, the bigger it is. With this one, remember the reason I use these two is because they're in the same period, right? So these both have 2 energy levels. Well, that's where electronegativity comes into, the ability to attract electrons. That's why this electronegativity is 1.0 and this one here is 4.0. Okay? Has a good ability to attract electrons. Not only electrons in a bond, but its own electrons too. It pulls everything closer towards it. Has a good chance of that because it just condenses in so much. Here, okay, Electronegativity, we can talk about that too. This is 1.0. I think this is 0.9. Okay. So once again, okay, the difference between these two is an extra energy level, right? Lithium's got 2 energy levels, sodium's got 3. Okay? So there's no surprise there probably. Sodium's actually obviously bigger. It's a physically bigger atom, and yes, it weighs more. That has really nothing to do with what we're talking about though. All right? Now, I want you to think about this for a second. If we're talking about the ability to share electrons, or in some cases maybe even steal electrons, we're going to compare, this is silicone here, there's its nucleus, and there's silicone's nucleus there. So I want to show you a little bit about what we're going to be doing here in the next little bit, and it's maybe, we're not even going to get this complicated, but just so you know. Those are both our silicones. We're going to compare, basically, cesium, and if you look where cesium is, okay, it's in period 6. And it's a metal, of course. We're going to compare cesium. We're going to compare fluorine. So here's cesium. Here's its nucleus right here. That's where all the protons and neutrons are. If we're going to do electrons, for cesium, we need 6 valence electrons, yes? It's in period 6, roughly. Yes? Do you agree? All right. So let's say 1, 2, 3, 4, 5, 6. Okay? So once again, think about the radius for this one. Obviously quite large, yes? Right? Pretty big atom. Here's silicone here, and silicone's got period 1, 2, and 3, yes? It's in 3. So here we go, 1, 2, those would be the outside electrons right there on that one. Okay? So if you think about the distance, right? Electronegativity, the ability of an atom to attract electrons in a shared bond. Shared bond, we're talking about valence electrons, yes? Outside electrons. Does cesium have a good ability to attract its own valence electrons for that matter? Does cesium want to attract that last electron, or does it want to kind of let go? Let go, right? Look where cesium is. Look how far away those electrons are, right? That one extra electron. If it lets go, it becomes like xenon, yes? Metals. Cesium forms a 1+ charge. It wants to get rid of that one electron. There's that one electron floating way out here. How well does this attract that? Not very good. How well does cesium attract silicone's valence electrons for that matter? How well does this attract this right here? Probably not very well either, right? Think about the distance between the protons, the nucleus, and the valence electron that it has, but also the valence electrons of silicone. That's quite a ways away. Look, right here. That's how much distance it's got to cover to even want to attract a silicone electron, for example, or give away an electron for that matter. Okay? In comparison, we said it's got 3 here, so there's 3 right there. Okay? There's obviously some electrons there. Here's fluorine. It's got 7 valence electrons there, sure. Here's the nucleus, the protons there and the protons there. How well does fluorine, how close is that nucleus to the valence electrons of its own? And not only the electrons of its own, but the valence electrons of silicone now in comparison. Pretty close, yes? So do you think that fluorine's going to have a good effect on the valence electrons, not only of its own, but of silicones as well? Oh, sure it will. Okay, because look at the distance difference. We're comparing this, right, to basically this, right there. Okay, so those protons, those protons there do have an effect over those electrons that it has on its own, but also on silicones, much more of an effect. Okay, And that's what we're going to talk about. I'm going to make it even simpler for you here on the next page here. Yeah. Which one? Okay, well, this is the nucleus. That's where the protons and the neutrons are. These are all the electron orbitals around it. Okay? So, you can read that, but basically that's what it says. Fluorine's going to have a significant effect on silicone's valence electrons. All right? Okay, so we're going to look at some different types of bonds here. And this is pretty important for the upcoming days. So you definitely want to make sure you understand what electronegativity is and what types of bonds can be formed, because this is going to lead into the second half here of what we're going to talk about. What kind of molecules do we have and what kind of forces are involved. And this is really like the beginning of the second half. And this is probably more so important than the first half so far, I would say. Ionic bonds, we already know, is a metal and a non-metal come close enough together. The non-metal will gain electrons, the metal loses electrons. Look, this is what you guys wrote for your quiz today, yes? An example of an ionic compound, a metal and a non-metal. You start with two neutral atoms. You show me electrons moving, okay, like so. I gave you a tougher one too that you guys studied in your notes, of course, because you guys are taking stuff home to study, and it's going to be more challenging. And, oops, and we'll put one there. Okay, so that sodium loses its electron and the chlorine gains that electron. Okay, so we get something that looks like that. Let's take a look at what the electronegativities of sodium, 0.9, let's write this down here, guys. Sodium is 0.9, and chlorine is what, 3.2, yes? Okay? So, we need to look at those electronegativities. What do these mean? Out of these two here, which one wants electrons more, sodium or chlorine? And this should not be a trick question for you. If it is, that's bad. Okay? Which one wants electrons more, sodium or chlorine? Chlorine, thank you. So, 3.2 basically indicates that it wants it with a force. You could say, you could use forces if you want to use physics kind of thing, and we're going to do a little bit of physics later on. But chlorine says, hey, I really want those electrons. I have electronegativity at 3.2. Sodium has only electronegativity of 0.9. If you think about the scale of electronegativity, which goes from 0 to 4.0, which reminds me of a song. What are you two? If you look on a scale of 0 to 4.0, okay, well, 0.9 to 3.2, that's a pretty big difference. Okay, you might say, well, how big a difference is that? Well, actually, you can just do this, and we're going to do this, so you might as well write this down. If you subtract those two, it gives you a total difference of about 2.3. Okay, now that's substantial. And basically what happens is, okay, what we're going to learn is when we're talking about bonds here, and I'll show you on the next page as well, when we're talking about ionic bonds, why do metals lose electrons and why do nonmetals gain them? Why don't they share them? Because that's what we've told you, right? True? Haven't we always told you that? Metals lose electrons, nonmetals gain them, yes? We've told you that. Why? Yeah. True. But why don't they share them? They could become balanced shared. Possibly, in some cases. Huh? No. Why are we gaining and losing? Well, because chlorine is so overpowering with its electronegativity, the ability to share those electrons. Chlorine doesn't have an ability, in this case, to share that electron. It just wants that electron. The 3.2 is so overpowering compared to the sodium 0.9 that it just takes that electron. Okay? In some cases, yes, they actually end up being shared. So when you look at some of these elements here, we're going to actually see that if you get close enough together in those differences in electronegativities, one atom can't take that electron from the other one. It doesn't have enough power to. It doesn't have that high enough electronegativity to take that electron and say, you know what, I'm taking you. Basically what's happened here is chlorine said, hey, I'm taking your electron, and sodium said, okay. Chlorine, I'm taking your electron. Sodium said, okay, and took it, right? So they don't share, right? There's a give and take there. Chlorine's strong enough to do that. But when you look at different elements, sometimes they're not strong enough to do that. That's when you get molecular types of compounds. Or that's when you get ionic compounds that almost act more like molecular compounds because the electronegativity isn't as great. Okay? So that's what we're going to do in the next day here or so. Okay? Here, nonpolar, you guys got to write this down here, nonpolar and polar covalent bonds. Before you start here, stop. Listen, there's two symbols here, right there, and you're going to be like, I don't know what that is. Well, those are both delta, is what they're called. I know you're thinking delta is the triangle. That represents a change. Change in temperature, change in something. We're not doing change here. This is not change. This means partial positive, partial negative, delta plus, delta negative. How do you write that? You might say, I don't know how, I can't draw that. Well, if you're a bandy, aka music, you would do like a music note is fine kind of thing. I just draw them like that. When they get messy, I end up like whatever, plus, and something like that, minus. Okay, they're like a fancy D kind of thing. So that's what that means. Okay, so just so you guys know when you get to that stage there. As long as it kind of looks like that, I'm okay. All right.